Beams have determinacy just like trusses, but beams are a little more complicated. The equation to figure out the determinacy of a beam is I equals 3 plus j minus r, where r is the number of unknown reactions and j is the number of internal releases. 3 gives us our three equations of equilibrium. J is the internal releases, R is the reactions. 3 plus J are our knowns or equations. R is our unknowns, which are the reactions. Now, this equation has the same pitfalls as an equation or anything else. It doesn't 100% tell you if something is determinate. It could be fooled with a mechanism. So if we had a beam that had 3 rollers, we'd have 3 reaction forces, we'd have no internal releases, and we'd have 3 equations of equilibrium. So we'd have 3 minus 3 is 0, and we'd say, oh, it's determinate. But we've actually created a skateboard with 3 wheels that can roll away. This is unstable. If something is unstable because of internal releases, we find this equation is less than 0 and it's unstable. And if it is greater than 0, we'd find that it's indeterminate and we couldn't solve for all the reaction forces. Now, we take just a simply supported beam. We have 2 reactions from the pin, 1 reaction from the roller. So R equals 3. We have no internal releases, so J equals 0. And we have our 3 equations of equilibrium. We have I equals 3 minus 3. That equals 0, so it's determinate and everything is okay. A little more about internal releases. Internal releases, or the J that we talk about up here, have to do with special things we add in the middle of a beam that release an internal force. So here I have an old style foldable measure. This is what they used to use in construction before you got a regular sliding tape measure. My grandpa gave me this. So if I look at an individual segment of this ruler, it is basically a solid beam. If I bend on it, it can't bend. I hold it fixed with this hand. Now, inside this are hinges. These hinges allow the beam to rotate. So when I apply a force here, it can freely move around the hinge. What this hinge is doing is causing the beam's ability to resist moment to go away. So when I apply a force, it causes a rotation where the beam can't resist moment anymore. So if we do an analysis right at this hinge, if we did a section cut and broke it apart, we would find that at the hinge, the moment has to be 0. Now, when we have as I said, when we have a hinge, we know that moment equals 0 at hinge. When we have a slider, the slider can resist moment, but the wheels go past one another. So we know that the shear equals 0 at slider. And an axial release, as I've shown here, tells us that the axial force equals 0 at, and we just call this an axial release. So what these internal releases do is they take away one of the unknown forces we have when we do a section cut. And we can use this to actually solve more complex beams. So here we have a fixed support on one side and a roller support on the other side. So a fixed support, we go back, put the sign convention in, gives us axial shear and moment reactions, or a force. We'll call this point A, we'll call this point B, we'll call this point C. We'll have RAY, RAX, and MA, and then we'll have RCY. And if we look at the number of reaction forces we have 1, 2, 3, 4. But we only have 3 equations of equilibrium, so there's no way that we can solve this just using our 3 equations of equilibrium because we have 4 unknown reaction forces. But we have the internal release hinge in the middle. If we go through our equation here, we'll find that R equals 4, J equals 1. If we do I is equal to 3 plus 1 minus 4, we'll find that this equals 0, and it's determinate. But it's only determinate if we take into account that internal release. Now, in order to take account of anything internal, we need to do a section cut. So that's what we're going to do. We're going to section cut right at B. That's going to leave us with 2 pieces of the beam. We'll have over here RAY, over here X, have A. Here we'll have RCY. Now, normally internal to any beam, we're going to have a shear force, an axial force, and a moment. And over a cut, since B is 1 point in space, so this is MB, AB, and VB, since they're at 1 point in space, they need to be equal and opposite. So VB, AB, moment B. Now, this encompasses all the forces, but since we have a hinge at point B, just like the ruler, this beam can't resist any moment at that hinge. So we know that the internal moment B has to equal 0. Now, if we look at each side of this section cut, we'll see that we have 1, 2, 3 unknown forces. Over here, we have 1, 2, 3, 4, 5 unknown forces. Right. We can apply our 3 equations of equilibrium to each side. If we apply them to the left-hand side first, we are not going to be able to solve everything. We have 5 unknowns and 3 equations. But 2 of those unknowns are carryovers from the right-hand side, where we only have 3 unknowns: axial at B, shear at B, and RCY. So over here on the right, we can solve for everything and take A sub B, and V sub B over to the left-hand side, and then we will only have 3 unknowns over here left. Again, this was only possible because we knew the moment at B is equal to 0. If there was a moment at B, we'd have 4 unknowns on the right side and 6 unknowns on the left side. We would not be able to solve for everything and bring them back and solve that. So in order to take advantage of the thing we know about an internal release, we need to make a section cut and then break everything apart and analyze it. Now, the one thing I forgot to add here was our load, P, which happens at L over 4 on the right-hand side. Now, if you're very astute, you'll realize that when I make this section cut, I have a vertical force VB, a vertical force RC, and a horizontal force AB. The A sub B and the V sub B combined behave the same way as a pin support, and RC is a roller support, and there's a load in the middle. This beam section that we have here behaves exactly like a simply supported beam with a point load in the middle. Simply supported beam with a point load in the middle is symmetric, and since it's symmetric, we know that the total vertical reactions has to be the total loads divided by 2. So RCY will equal P over 2. BB will also equal P over 2. And A sub B will equal 0. Once we know this side, we can know that A sub B equals 0, and V sub B will be P over 2 acting down. Let me clear out some of this clutter that I've created for myself. Now, if you want to see me solve the reaction forces on a simply supported beam, you can go back to one of my previous videos. And also in one of my previous videos, I solve a cantilever with a point load on the end. And if we look here, VB is a force of P over 2 acting down, and then we have the fixed support on the left-hand side. This left-hand side of the beam acts just like a cantilever with a point load on its end. For that, we found that RAY is equal to P. In this case, it'll be P over 2. RAX is equal to 0. And the moment is equal to the applied force times the length. So in this case, MA will be P over 2 times L over 2, or PL over 4. So by doing this section cut and looking internally, that allowed us to determine our reaction forces. Now, we can take those reaction forces and move forward and know that we have a moment here of PL over 4. We have a vertical reaction force here of PL over, or not PL, P over 2. Here we have a vertical reaction force of P over 2. And here we have an axial force equal to 0. From this, we can go ahead and draw our shear and moment diagram. Now, for our shear and moment diagrams, the shear diagram moves with forcing function. In this case, we only have point loads, and these point loads cause jumps in our diagram. Shear and moment diagrams need to begin and end at 0. So on the left-hand side here, we start at 0. We jump up a value of P over 2. So we go from 0 to P over 2. Since there's basically no forces from here to here, the shear diagram will remain constant. At the load of P, we're going to jump by a total of P. So go from positive P over 2 down to negative p over 2. Since there's no loads from here to here, we're going to stay constant at p over 2, and then our reaction force is going to jump us from minus p over 2 up to 0. So our shear diagram begins and ends at 0 and is just two piecewise constants. So we can write our piecewise equation as it's p over 2 for 0 is less than and equal to x is less than 3pl or 3l over 4. It is minus p over 2 from 3l over 4 is less than x is less than and equal to 0. And we have a jump here at 3l over 4. Now, since our shear equation is made up of two constants, due to our integral relationship, our moment equation is going to be made up with two lines. And if you integrate a constant, you know the constant becomes the slope of the line. So for the first 3/4 of the beam, we're going to have a positive slope of p over 2. For the last quarter of the beam, we're going to have a negative slope of p over 2. Just constructing it from the things we know, we see that we have a negative moment of PL over 4, negative reaction moment of PL over 4 at the end. So we're going to go from 0 to minus PL over 4. There is another, well, we'll come back to the other special thing. So for our first piece of our moment equation, because we're going to have two, we can say that m1 is going to equal the integral of p over 2. We know that m1 will equal px over 2 plus c. Px over 2 is just that p over 2 becoming the slope of the line. We know the moment at 0 equals minus PL over 4, so that C is going to equal minus PL over 4. And our first moment equation is going to be PX over 2 minus PL over 4. If we use this equation and plug in 0, we get our minus PL over 4. If we plug in 3L over 4 for our moment equation, 3L over 4 will be P 3PL over 2 times 4 is 8. So minus PL over 4. So this is the moment at 3L over 4. The common denominator here will be 8. And this will equal PL over 8. So the moment for the first portion will be a straight line going from minus PL over 4 to 3PL over 8. And it will have this equation. The second part of our equation, and I'm going to clear up a little space, is going to be linear, but it's going to have a slope of minus p over 2. So m2 will equal the integral of minus p over 2. If we integrate this, we find that m2 equals minus px over 2 plus c. Now, we already know the moment at this point here is PL over 8, and we can use that to solve for C, because our moment and shear diagrams need to be continuous. So we can say that M2 at 3L over 4 is equal to PL over 8. We can say PL over 8 equals minus P over 2 times 3L over 4. That will equal, or plus C. This is PL over 8. This is minus minus 3PL over 8 plus C. C will equal 3PL over 8 plus PL over 8 gives us 4PL over 8, which is PL over 2. So our second moment equation is PL over 2. So plug that in here and give us our second moment equation of PL over 2. So now we can plug in numbers like I did previously. If we plug in 3L over 4 for x, we find that M2 equals PL over 8. If we plug in L for x, we have L here, so we have minus PL over 2 plus PL over 2, which equals out to 0. So our moment then will go from PL over 8 to 0, and the equation for this line will be minus P over 2 plus PL over 2. Now, an important thing happened here. If we look at our hinge and come straight down the best we can, will look like something special happened, and something special did happen. If we plug L over 2 in for x in equation M1, we will get PL over 4 minus PL over 4, which is saying that at the hinge, moment is equal to 0. And that is what it had to be, because the beam cannot resist moment at that hinge at all. So internal releases give us internal conditions that we can use to solve problems.